So, can you? So our next speaker is Sara Marziali, and she is going to talk about varying decompositions of special binomials.
Okay, so thank you for the introduction. I'm really glad to be here to present this work. This is a joint collaboration with Professor Piantini and Professor Cosmullo that I'm here, so I thank you for being here. And today I'm going to talk about varying decomposition of special binomials. So before starting the presentation, I would like to briefly overview what we are going to see today. Most of the topics are already in touch, but anyway, I want to briefly introduce the varying decomposition in order to, so that everyone is on the same page. Then I want to introduce our starting case, which is the monomial case. Then I will introduce our case of study, the main results, and finally I will give you a sketch of the tools, right, and the tools that we will exploit. So first of all, we deal with varying rank. Okay, so the idea is that we are considering the space of homogeneous polynomials of degree V on a vector space V of dimension n plus 1, and we let the star be its dual space. Okay, so in general, if we take a polynomial of degree V, its varying rank is a minimum R such that F can be decomposed as the sum of D powers of linear forms. Okay, and what is interesting regarding the varying rank is that it has a really nice geometric interpretation. Okay, so the idea is that if we consider the veron as a variety, and then the varying rank can be seen in equivalent way as the minimum number of points such that P is spanned by the set of points. Okay, and this means that we can consider this set of points, that in this case we call X, which can be called as a varying decomposition of our polynomial. So before moving forward in our analysis, I would like to recall the state of the art of this kind of problem. Okay? In general, computing the varying rank of polynomial is extremely hard. There are known results. For instance, we have a result from Alexander Ishvitz in 1995, which determined the varying rank for generic polynomial. Then we have to wait up to 2019, when Galuppi and Mella provided a complete classification of generic polynomials with unique minimum varying decomposition. Another case of study is when we study generic polynomials in which the varying rank is smaller than the generic one. And here we have results from Contini, Cogliano, and Van Norman, which show that all of these cases have unique decomposition up to 3 cases. And to tackle this kind of problems, when the rank is extremely small, that we can use somehow eigenvalues. And maybe what is the most interesting for our case of today is the case of some special polynomials. Okay? And in particular, I want to recall the result obtained by Cardini, Catalizano, and Torinita in 2012, which completely provide the characterization of the varying rank in the case of monomial. Okay? The basic tool for this analysis is the polarity theory that I will introduce in a few moments, even though, I mean, he has really talked a lot about it. But before doing this, I want to record the results, just this one. Okay, so if we have a monomial n, which can be written as x1 to the power of 1 up to xn to the power of n, then its varying rank is given by 1 over the smallest power a1 plus 1 times the product of all the powers plus the ai powers plus 1. Okay, where we imagine that all these powers from a1 to an are increasing in big order. So, as I was mentioned, one of the main basic tools for this type of study is a polarity. Okay, so before I want to record this ring in a dual space of variables, and this ring has 2 different roles. Okay, it can be seen as the homogeneous coordinate ring of the projective space, and at the same time, it can be considered as the ring of differential operating with constant coefficients. Okay, and now for every polynomial, it is possible to associate an ideal, which is the so-called hypolaritor, which is the manipulator of F, which is a set of differential operators D, such that the result of differentiation of the polynomial with respect to this D is equal to 0. Okay? So from now on in the following, I will indicate with capital letters, so from x0 to xn, as the basis of the dual space we start, and x small to xn as the basis of the vector space. Really. And then it holds that, for instance, xj of xi is the delta depth of ji. Okay? And this is the basic tool that we use, which is the polarity lemma. So the idea is that if we have a polynomial f of degree d, again, and we have a set of points x indicated by L1 R, then it holds that these points provide a decomposition of the polynomial. So we have that f can be written as the sum of powers of the linear form multiplied by some coefficients, lambda 1, lambda r, if and only if the ideal of x is contained in the liquidator. Okay, we have a double implication, so we have complete characterization. Now we are ready to start with, which is the starting point of our analysis, which is the monomial case. Okay, and in this slide, I want to report the main results, which are provided by Carmini, Caterizano, and Tremita, and by Yushinska, and in particular, if we consider an integer positive number k, and we take g to the monomial degree of degree k times n plus 1, we have the construction of the apolar idea, so the vector, which is determined by the variables of the space, of the basic space. Then we have the computation of the Warring rank, which is equal to k plus 1 to the power of n. And finally, it also defines a minimum decomposition f of this monomial of length, as I was saying, k plus 1 to the power of n, given by the complete intersection of Ix. Okay? So what is important about this theorem is that basically it's a complete characterization, in the sense that all minimum decomposition that we have for the monomial arise in this way. So now that we have our starting point, we can introduce our question. Okay, if I know what is the Warring rank for a polynomial, I can ask what is the Warring rank of this polynomial f, which is given by the polynomial plus a linear form in power n plus 1 times k with a coefficient lambda. Okay, so why I start with this case? First of all, because for n, for instance, equal to 1 and equal to 2, I can perform the computation. Okay, and the case for n equal to 2 that we will see in the following is already seen. Then, because it's the first case beyond the pure monomials, for instance, the sum of these terms. And finally, because we already have the characterization of the rank for binary binomials given by Aristotelian. Okay? But this is not the only question, the only reason for which I want to study this kind of polynomials. Okay? The first one, and as a motivation, is a computational one. Okay? Indeed, you have that these polynomials, which have this form, can define a new model of computation, which is the so-called product plus power model of computation, which turns out to be equivalent to sigma, lambda, sigma circuits. Okay? And these are exactly the model which are usually exploited for computing the border Warring rank. Okay? And the other motivation is more physical, because we have some kind of physics states, the liquid state I've already seen, which corresponds to monomial of this kind. Okay, so computing the Warring rank of this monomial corresponds to computing the minimal number of product states which are needed to define this state as a superposition. Okay, so now I want to show the main result that we obtained in our work, and I will introduce this for the case when n is equal to 2. General, and then we have that if k is an positive integer, in particular I take k greater than 2, since the one case is mixed size, and we have a polynomial f of these four, okay, so three variables and plus linear form to power 3k, then the following holds. The first case is when all the three coefficients on the linear form are different than 0. In this case, there exists just one lambda 0, so a coefficient such that the Warring rank of f is equal to k plus 1 squared minus 1 if the coefficient is exactly lambda 0. And in the other case, when lambda is different than lambda 0, then the Warring rank is k plus 1 squared. And moreover, whatever is the value of lambda, we have that there is a unique minimum decomposition. And the other case, of course, is when there is at least one coefficient which is equal to 0. Okay? So in this case, what happens is basically that the Warring rank of the polynomial increases by 1. And this has to be, for instance, to the problem of forbidden logic, in which we want to decompose polynomials by avoiding. And the interesting thing is that in order to prove this theorem, which is our main result, we actually prove another theorem, which is the technical form of our proof. So basically, we prove a second theorem, which is this one, which again I show for the case n equal to 2, such that once we have proven this theorem, we have directly the proof of the first one. Okay? So if we take a monomial G of the form x0 to power k, x1 to power k, and x2 to power k, then we can show that G cannot have a redundant variable decomposition of length k plus 1 squared plus 1. Okay? Because if we consider f to be a polynomial, as I was mentioning before, so given by the sum of G plus the power of the linear form, and we have that the rest of the polynomial f is k1 plus 1 squared, then it means that a minimal decomposition of f together with the point L provides a decomposition of length k plus 1 squared plus 1 of G. Okay? But then this decomposition is automatically redundant, where here with the redundant, I mean that all the coefficients are different. We will prove that this is not possible, so that if we assume that such a decomposition exists, we get a contradiction, and this also implies the inclusion of theorem 1. Before moving to the basic step of the proof, I want to mention that all the cases beyond the one put in theorem, introducing theorem 1, so for instance, when n is equal to 1, or k is equal to 2, or k is equal to 1, still are true. For instance, here we cover exactly the decomposition provided by Stenger and Pazzotti, and the same happens for probabilities. Okay, so the same happens if we assume that k is equal to 1, and we get the result over the red. In particular, we have that here, if all the coefficients are different than 0, then the Worley rank of the polynomial can be 3 or 4, while if at least one coefficient is equal to 0, then we have exactly the generic. So now I want to sketch what is the proof strategy of this theorem. Okay, the basic tool that we exploit is the Hilbert-Wurth matrix. And before to introduce this kind of matrix, I want to give you an idea of what is our set. So we have a polarity theory which characterizes for us decomposition. So the idea is that we can take two decomposition of our monomial G. We call them x and y, which consist of these joint points. And we assume that x has length k plus 1 squared and y has length k plus 1 squared plus 1. Okay? Now, by using this Hilbert-Wurth theorem, we will show that since x and y lie in a complete intersection of type k plus 1 and 2k plus 3, then we will be able to compute the Hilbert-Wurth matrix of y. Okay? Before going on with the proof, for people who are not familiar with the concept of Hilbert-Wurth theorem or Hilbert-Wurth matrix, I want to recall the result. Okay? If we take a set of points, okay, let's say x in P2, then we can compute the minimal pre-resolution of the ideal x to have this form. Okay, so basically we can say that there is a sort of map between our modules, which is determined by a matrix of size beta times beta minus 1, which is here, which is the so-called Hilbert-Wurth matrix. And the idea is that the ideal of x is generated by exactly the beta minus 1 minus of this matrix. Right? So the idea is that we are trying to compute linear algebra over the polynomials. Okay? And once that we have this Hilbert-Wurth theorem for set of points in P2, we have a lot of interesting properties. For instance, here I want to recall the Kari-Bahara property, which is something that we use in proof, but in general we can provide several properties for the ideal of points. And in particular, we have that if we have this set of point x, and we take any form of degree d, which vanishes in the total of the quality of point minus 1, then we will also have that this property vanishes on the last point. Okay? So once we have introduced this theorem, basically the take-home message is that whenever you have a decomposition provided by a set of points, then you can construct this Hilbert-Wurth matrix, okay? Which gives some ideas on the properties of these points. So now we're ready to move forward in our proof, right? So we have the Hilbert-Wurth theorem, but we also have a polarity. I already introduced a polarity. But this says that we can characterize the decomposition, let's say y, of our monomial G as a set of points. And in particular, as a set of points whose idea is contained in the nucleator. Okay? And in particular, this ensures us that there is a decomposition G of length k plus 1 squared plus 1. And the other tool I want to exploit is the Hilbert function, okay, which is a characteristic of a set of points that again is the following. And by comparing the first difference of the Hilbert function with our y decomposition with another decomposition of length k plus 1 squared, which is the set of points X, then we will get some strong condition of the interaction between the points. So what is a sketch of the proof for our theorem? So first, I introduce the Hilbert function of a set of points. So if we take X to be a set of points and I to be the ideal, we will call X, then the Hilbert function of X can be seen at degree T as the codimension of the ideal at degree T. Okay, and in the same way, we can define the first difference of the Hilbert function as the difference between the Hilbert function of degree T minus the Hilbert function at degree T minus 2. In general, the Hilbert function can be seen as a box plot. Okay, so we can represent this function with these plots, which represents the point of the decomposition. And in our case, if we assume that for the sake of the proof, the k to be equal to 4, we let that our monomial can be written as x0 to the power 4, x1 to the power 4, and x2 to the power 4. So if we have x and y to be due in redundant decomposition with these points like disjoint, then we have that k plus 1 squared is equal to 25. So we have 25 points in X, which are represented by this point blue. And we have in the same way 26 points for decomposition Y, which are represented by these points in red. Okay? We have strong conditions for the Hilbert function. And by studying the Hilbert function of this set of points, we conclude that the set of points in X union with points in Y, union L, which is a length 4 scheme, which lies in a line, which are these 4 gray points here, produce a complete intersection of type k plus 1 to k plus 3. Right? So we have a complete intersection of 5, 11 points, which contains all the points of X, Y, and L. And this is the box plot of this Hilbert function. But now we know that by the Hilbert-Wurtz theorem, we can associate to each decomposition of the monomial T a Hilbert-Wurtz matrix, okay, which is nothing but a map between monomials. And since X and Y are assumed to be the composition of G, then we can retrieve their Hilbert-Wurtz matrix. In order to do this, we start from the fact that we lie on a complete intersection, hence we compute the Hilbert-Wurtz matrix of this set of points X. We compute the Hilbert-Wurtz matrix of the set of points X in L, and this will allow us to retrieve the Hilbert-Wurtz matrix of set of decomposition Y. Okay? Now, with a lot of computation, we obtain that actually Y, given by this Hilbert-Wurtz matrix, is nothing but the union of the points of X, union 1 point with 0. Okay? And this is against our hypothesis, which was that the composition of length k plus 1 squared plus 1 was not redundant. Okay, so Y cannot be redundant, and then we have a contradiction of the hypothesis, and this means that in this way we prove the second theorem, which also implies the first one. Thank you for the attention. If you have any questions.
Well, thank you. And now time for questions.
Maybe you have already said it more than once, but so in this Hilbert-Wurtz theorem, like what exactly about it is the thing that makes it true about this?
Yeah.
So you said that, for example, the idea is permanent and so on.
Yeah.
So which is like the key property that you're using and that doesn't happen, for example, absolute freedom.
You mean that it goes for points in P2?
Yeah, the theory is just for these.
Yeah, yeah.
And so, which is a thing that you need so crucially it doesn't.
I'm not.
I can say so.
Yeah.
So there are like several things that you use about P. So one thing is like can you go back the slide of the graph? No, the next. One thing is that in P2 you can obtain strong conditions. So like essentially you can force the Hilbert function to take place. Force the Hilbert function of the union to take place. And to do this, you have to use some things that only hold in P2. There is like some regularity statement or something like that. And the other thing is that the Hilbert-Burch helps you because you get this matrix. Like, can you go to the next one? So you end up knowing that this y, the idea of this y, is the determinant of a matrix that has those degrees. That 4, 4, 5, 1, 1, 2 are the degrees of the entries of the matrix. But then you can play a lot with the entries of the matrix. For example, like 1 and 1, you can essentially normalize them to be two variables. And then you can use those two entries to cancel those variables in the rest of the matrix, doing rows and column operations. And that forces this idea to be very special in the end, and when you get to the end, yeah. So it's kind of, there are both theorems that only holds in P2 and a very special structure of the idea that you get in the end. The other thing is also like complete intersections in P2 are just intellectual.
So it goes. So the idea that we use things in P2 and the same time.
You plan to apply this to other type of binomials?
Yeah, it's not easy. At the beginning, we were trying with the bunch.
Yeah. It's hard.
Yeah.
Yeah.
It's hard because for other, okay, we don't know what the rank of monomials, but let's pretend we know. And for these monomials, where all the exponents are the same, those are the only ones for which rank and where the rank is the same. If we pretend to know what the rank. And if you go to some other monomial, this construction will find the cactus decomposition that is short, that is the one that gives you the order rank decomposition. And that messes up all the numbers. You're fighting against something that is too small, that is not at the length that we are working.
We were trying at the beginning for most cases.
Yeah.
It's not easy.
Thank you.